this video, we're going to discuss the ideas of power in chapter 6.7. Definition of power, the average power P is the average rate at which work W is done and is obtained by dividing W by the time T required to perform the work. The equation that goes with that definition looks like this. Average power, that line over the top of the P means average. Average power equals work over time, which is W over T. It's the rate that work is accomplished. It's measured in joules per second, or a joule per second is the same thing as a watt. So you'll see it typically in watts or joules per second. So you'll also see power as being the change in energy over time. It's because there's different kinds of energy we'll use in the future: electrical energy, thermal energy. So, but today, for our purposes now, we're using mechanical work. We are looking at. Here's a situation. I want you to. We'll read through this together, and then you think of an answer, and then we'll pick which one is correct. You can pause the video. Engine A has a greater power rating than engine B. Which one of the following statements correctly describes the ability of these engines to do work? A. Engines A and B can do the same amount of work in the same amount of time. B. In the same amount of time, engine B can do more work than engine A. C. Engines A and B can do the same amount of work, but engine A can do it more quickly. So you decide which one you think you should pick. The answer is C. Power is the measurement, is the calculation that tells us the rate that work can be done. So C talks about rate. B, if you pick B, you're talking about the amount of work. And that's not what that's not what power is about. Power is the rate that work is being done. In other words, how quickly is work being accomplished. So if we start off with this equation, power equals work over time, we know that we can write work as force times displacement, F times S, all over time. And we can now write average power equals force times the average velocity, because we know displacement over time right here, this displacement over time, is velocity. So we have force times velocity. An example problem would be a 1.1 times 10 to the third kilogram car starting from rest accelerates for 5 seconds. The magnitude of the acceleration is 4.6 meters per second squared. Determine the average power generated by the net force that accelerates the vehicle. So pause the video now and see if you can come up with that answer. So what we have here is, using F equals ma, we can find the force acting here. We have mass times acceleration. It's 1.1 times 10 to the third kilograms times the acceleration of 4.6 meters per second squared gives you a force of 5,060 newtons. And we know that average velocity is equal to half final velocity if our initial velocity was 0. We've done that in our labs before. So average velocity is half the final. If we use the equation V final equals V initial plus AT, and we plug in our V initial is 0, our acceleration is 4.6 meters per second squared, our time is 5 seconds, we end up with a final velocity of 23 meters per second. Now if we use the equation average power equals force times average velocity, we can use our 5,060 newtons we used in F equals ma. We have 11.5 meters per second is half of 23 meters per second. We find our final velocity to be 23, but the average is 11.5. So that ends up, when you calculate that, to be 5.82 times 10 to the fourth watts, which is about 78 horsepower. Another problem we have here is a 73 kilogram sprinter starting from rest reaches a speed of 7 meters per second in 1.8 seconds. It's a negligible effect due to air resistance. The sprinter then runs the remainder of the race at a steady speed of 7 meters per second under the influence of a 35 newton force due to air resistance. So in the beginning, there's no air resistance, but then once we reach a speed of 7 meters per second, we have a 35 newton force of air resistance. Calculate the average power needed to accelerate the runner and then to sustain the steady speed at which most of the race is run. So pause the video and see if you can come up with the answer for A and B. And I'll go over that now. So that's B. Okay, here we have power equals work over time. And in this case, our net work is our change in kinetic energy. So we plug in our kinetic energy. Since kinetic energy initial is 0, change in kinetic energy is our kinetic energy final, 1/2 mv squared. So for our work, to get up to that velocity of 7 meters per second, we use 1/2 mv squared. Plug in our values, plug in our time of 1.8 seconds. We have 990 watts. And if you want to convert that to horsepower, that's what it looks like. We have 990 watts of power to get up to that certain speed. Now we're going to go ahead and do part B. And we're going to use the idea of power equals force times velocity. We went at an average velocity, a constant velocity of 7 meters per second against a force of 35 newtons. So it took 250 watts to sustain that steady speed against that force of 35 newtons of air resistance. And that was 0.34 horsepower. So to get up to that speed took more power than it took to maintain that speed. Now we're going to talk about work done by a variable force. The work W done by a constant force is given by the equation 6.1 as, we've seen this equation before, work equals F cosine theta times S. Quite often situations arise in which the force is not constant but changes in the displacement of the object. For instance, figure 6.2 A shows an archer using a high-tech compound bow. And we have the graph of this. We see where the force is not constant. The force is changing all the time. Our graph is F cosine theta on the y-axis and displacement S on the x-axis. The reason why they put F cosine theta here and not just F is because they just wanted to make sure we understood that the force they're talking about here is parallel to the displacement. It's the component parallel to displacement. In order to find the work accomplished, you simply find the area under this graph. So the rule here is that the work done by a variable force moving an object is equal to the area under a F cosine theta versus S curve. Now, the reason why that is because if you want to solve for work, you just do force times displacement. And to find area, you basically do base times height. Now, depending on the situation, you have to, whether it's a triangle or some other shape, you have to be careful. You can't just say base times height, but that's why we go with the area. So here's an example of a situation we have to use a graph to solve our network. The graph below shows the component F cosine theta of the net force that acts on a 2 kilogram block as it moves along a flat horizontal surface. Find A, the net work done on the block, and B, the final speed of the block if it starts from rest, as S equals 0. So whenever we find area, it's going to be the area down to the 0 line. So here's our 0 line, and this area here is going to be positive area. There's no area under this line. There's positive area here, and here there's negative area. So we have to subtract away from that positive area. And then here there's no area again. Because remember, it's always from the line to 0. So we find this area, subtract this area, and that will give us our net work. So the first area there is 8 joules here. This area down here is -2, so it's a total of 6 joules. And now we want to find the net work done on the block, or we want to find the final speed of the block. We're going to use the idea that net work equals a change in kinetic energy. And our initial kinetic energy is 0, so our final kinetic energy will equal 6 joules, will equal the net work. So our work equals 1/2 mv squared. And when we plug in our values and solve for our final velocity, we get 2.45 meters per second. So we learned that work, or the power, equals the rate that work is accomplished. And we also learned how to solve for work with the area under a force versus displacement graph.